Hello everyone, today I'm going to present our work of a paper Approximate feature adaptive rendering for subdivision gradient meshes. Basically, our method is to create vector images using less dense meshes. Here's a nice example. On the left is a pair that we want. In the middle is the mesh created by our method. On the right is the mesh created by traditional method. Apparently, the mesh of traditional method is much more dense than that of our method, right? So let's begin our story. When we see a vector image, what comes into our mind is gradient mesh, and the most popular tool based on gradient mesh is Adobe Illustrator. Gradient meshes are a powerful vector graphics primitive for creating scalable vector graphics. Traditional gradient meshes, its vector primitive is defined by a regular rectangular mesh. Colors and color gradients are associated with the mesh control points. The user can assign colors and color gradients to the mesh. It's clearly that the use of regular rectangular meshes somewhat restricts artists designing the mesh, because you can, with some shapes, you cannot just use one single rectangular mesh to create them. You need to overlay several gradient meshes to get the shape. Like this banana, there are several meshes overlaid together actually. In previous work with subdivision gradient mesh, the restriction of rectangular gradient meshes is reduced. The method allows artists to create gradient meshes of arbitrary manifold topology. First, there is an original polygon coarse mesh. As you can see, the butterfly, the mesh contains polygons, so it's more convenient to create any shape you want. And then with this coarse mesh, we do a ternary subdivision to it. Then Catmull-Clark subdivision, we get a refined Catmull-Clark mesh. With this refined mesh, we can edit the shape and the colors in details. So as you can see, we can edit this butterfly coarsely also in details, and finally get a colorful full of details of butterfly. Ternary subdivision is the first operation. For example, we have a pentagon with 5 original vertices associated with 5 different colors. Ternary subdivision is to add a ring of vertices around each original vertices and assign them with the same color. Then after Catmull-Clark subdivision, we can ensure the limit color surface interpolates the color of the original control points. And you could consider these new points as color gradient constraints. You can adjust these new introduced vertices to get larger or smaller influence of the original vertex color. So in summary, ternary subdivision ensures the color of the original control points are interpolated, and users can adjust both the color and the shape with these new points. This is the rule how we do the ternary subdivision. How do we get the new points? It's very easy. New edge points are just evenly placed along the edge. New face points are got from linearly interpolation. So I put the formulas here for you to refer. After the single ternary subdivision step to the input mesh, we apply Catmull-Clark subdivision to the mesh. This ensures an almost everywhere C2 continuous color surface. This is an example of a pentagon. On the left is the mesh after ternary subdivision, and the middle is the mesh of one step of Catmull-Clark subdivision. On the right is the mesh of two steps of Catmull-Clark subdivision. You could see the Catmull-Clark subdivision very clearly. One pentagon comes to 5 cores, then 20 cores. And this is what Catmull-Clark subdivision does. So what I just presented is previous work. It's what's been done before, and it's traditional method. It supports all these nice features listed here, but it is not efficient. It creates meshes which are too dense. Although the refinement are local, it forces you to do global subdivision, which is not efficient. If you only want to add a small detail, like the small yellow point on the strawberry here, you have to subdivide the whole mesh. So ideally, if we want to add a local editing, we only subdivide locally and don't subdivide other area. So how do we improve on this? We use the idea from FAS-Feature adaptive subdivision. Our method is inspired by this computationally efficient method to evaluate the Catmull-Clark limit surface, including boundaries up to machine precision. The mesh is iteratively subdivided only in the affected vicinity of irregular features, while the regular patches are always directly rendered as bicubic patches. Special transitional patches are required to avoid cracks between adjacent patches of different subdivision levels. This figure shows 3 steps of this FAS idea. There are 4 irregular vertices whose valencies are not 4. So FAS only subdivides around these 4 irregular vertices. We borrow several techniques and ideas for real-time approximation of Catmull-Clark surfaces using hardware tessellation. Patches used in these techniques are called Approximate Catmull-Clark patches. I will call them ACC patches for short. Prime examples of approximation schemes are ACC1 using bicubic patches and ACC2 using Gregory patches. And this is an example of an animal rendering using ACC1-Bicubic patches. On the left, it is a Catmull-Clark patch structure. The gray patches contain only valence 4 vertices. Green have 1 extraordinary vertex and blue have more than 1 extraordinary vertices. On the right, it is a geometry patch approximation using ACC1. An alternative to ACC1 as a computationally efficient method to approximate the Catmull-Clark limit surface is ACC2-Gregory patches. The first image is an original control mesh. Regular faces are colored in gold, irregular cores are colored in purple, triangles are colored in green. The second and the third images show the parametric patches generated. Gregory patches are used to render the purple faces, the irregular cores faces. The final image is the same surface with a displacement map applied. So our strategy is like a hybrid solution. For each regular face in the mesh, a bicubic patch ACC1 patch is constructed. These patches reproduce the Catmull-Clark limit surface exactly. ACC1 patches contains regular patches and special transitional patches. As you can see, this beach ball mesh, most faces are rendered with ACC1 patches. These faces containing triangles are also ACC1 patches, but they are transitional patches. I will introduce transitional patches later in detail. Also, in this example, as you can see, there are several irregular faces around the center of the ball. Only these faces are rendered with ACC2 patches. So this allows us to do global subdivision, so that mesh created by our method is less dense than global subdivision. So here's a summary of our algorithm. It's inspired by FES, but it has difference with FES, or you can see improvements over FES. Similar to FES, at each level, we determine which faces to further subdivide. Faces that do not require further subdivision are rendered using bicubic patches or Gregory patches at their terminating subdivision level. FES keeps subdividing the mesh around irregular faces at each subdivision level until tessellation of the newly generated patches only amounts to evaluating the corner positions. In our algorithm, we introduce the concept of affected faces to determine at which subdivision level to terminate subdivision. I will explain this in detail. The key in our method is how we determine which faces to further subdivide. We define faces that need further subdivision as affected faces. There are three kinds of cases. Edited faces. Well, this is simple. If you change something of a face, geometry or color, then the face is defined as an edited face. As you can see, geometry edits affects a two-ring neighborhood, and color edits affects a three-ring neighborhood. Irregular faces, simple either. Non-quadrilateral faces and faces defined by non-four valency vertices. The last one, affected faces coinciding. Suppose you move a point colored in blue. There is irregular faces near it. Then there will be artifacts around these irregular faces. You can see these artifacts very clearly in the color map. Yellow means 1, blue means 0. So if you can see obvious yellow area, then it means the artifacts are big. So in this case, we choose to subdivide all the neighboring irregular faces around this affected irregular face. This is called coinciding. After coinciding, the artifacts disappear. We also have an efficient and smart way of index mapping related to hierarchical edits, but I'm not going to talk about this. It's too much in detail. Please read our paper for details if you are interested. For better understanding, let's see a simple example. This is a chord with 4 original vertices. Let's say I move one vertex at subdivision level 1. Then at subdivision level 0, after ternary subdivision, there are 9 chords. The red one is the affected face. It should be further subdivided. 2 yellow chords around it are transitional patches. The green chords are regular faces, which are rendered with ACC1 patches. At subdivision level 1, the affected chord is further subdivided into 4 chords and then rendered with ACC1 patches. Similarly, if I change a color of one vertex of this chord, there are 4 affected faces. They should be further subdivided. 4 yellow chords around them are transitional patches. The green chord is regular patch, which is rendered with ACC1 patch. At subdivision level 1, the 4 affected chords are further subdivided into 16 chords and then rendered with ACC1 patches. In order to deal with the T-junctions produced by adaptive subdivision, FAS produces transitional patches which connect patches at different levels of subdivision. These transitional patches are simply regular patches. Due to symmetries, this results in 5 different template transitional patches. Transitional patches are colored in yellow. Patches belonging to the current subdivision level are colored in green. Patches belonging to the next subdivision level are colored in red. Our program supports sharp color transitions. As you can see, this simple example, but sharp color transitions introduce dot vertices. The 2 dot vertices are circled in yellow. Dot vertices would introduce artifacts. So please see this artifact corresponding to dot vertices. They are visible around the color edit points. The resulting artifacts are very obvious, also shown in this plasma color map. Yellow means 1, blue means 0. One way to resolve this issue is by color editing the remaining vertex sectors around the sharp corner with their current color. As you can see, the circled area. So this greatly reduces artifacts caused by dot vertices. You will not see obvious artifacts after this operation. Okay, it's demo time. So the demo I show is the cherry model. At subdivision level 0, let's closely adjust the shape and the color. After high levels of editing, we come back to subdivision level 0, bend the stalk to the right. At subdivision level 4, we add some details. The water drop, we add a reflection point here. Careless geometry editing may lead to self-intersections. So to prevent this happening, we implemented self-intersection prevention feature. Our method has high efficiency compared with global subdivision method. With this cherry model, the x-axis represents the same number of triangles because data is tessellated into triangles after tessellation. So we use this number to compare. You can see our measurements. The average frame time is greatly reduced when the number of triangles are huge. In conclusion, our algorithm has these nice features listed here with improved efficiency. Thanks for listening.